Good evening, everyone. So I think we need to be going ahead with the online this lecture series and continue to finish up with the electricity and magnetism course. And this lecture series will largely cover the magnetic fields. Now we'll be dealing more about magnetic fields, forces between current elements, definition, Barr-Savart law, some examples. Then we're dealing with magnetic moments, Ampere's law, some examples on that, and also we'll be dealing with vector potential for magnetic field. We will go into magnetic properties for matter, electromagnetic inductions, circuits, some examples with network theorem. A large part of what we'll be lecturing here is from Griffith, and that's a very good book to follow. I recommend. Now, before we get into the complicated aspects of electrodynamics, I'd be definitely expecting that you already know some about electrostatics. And before that, definitely you know something about the vector analysis, which should have been in your semester one classes, sometimes in a much more preliminary classes than that. But still, we need some understanding about this one, so I'll just give it one short lecture on this one. To start with, we need to understand what is a gradient. So basically, the mathematical expression is delta t, which is expressed this way. And it's basically it. So a gradient converts a scalar, where t is a scalar and delta is an operator. It converts the scalar into a vector. And basically it gives, so the direction of the vector is the direction of the maximum increase of that function, whereas the magnitude gives the slope, the rate of increase along with the maximum direction. So it generally is given by this one. In case of vector, like for divergence, so the mathematical expression is something like this, whereas v is a vector. So a dot product with delta with a v is written like this. So it actually converts a vector into a scalar. Now, physically, vector gives you an idea about this physical quantity like v here. It's actually coming out or spreading out from a point. Whereas something which is a vector and it's actually circulating, some vectors have this property of circulating, can be expressed in terms of curl. And it's mathematically written like this. This is a vector with components. And its geometrical interpretation is, it's something like it's curling around or it's rotating around something. So before I go into this one, let me go back to this one more time. A good example for gradient is temperature. Temperature is a scalar. So when we have to talk about the difference of temperature within a room, or say in terms of height, so when you increase the height, you go say to a mountain and all that, what happens is, like, because of the increase of the height, the temperature goes down. So in this case, the temperature does have a direction. So if we go up, temperature actually goes down. So here the gradient of the scalar, which is the temperature. So there is a gradient. There is a difference between the beginning and the end, which is the height. And and the direction of the maxima, like when it's increasing, is the direction of the gradient. So in this case, if you go up, where the temperature is reducing, is actually a negative gradient. Whereas for divergence, it's more, the example are like something like flowing out, then the divergence is positive. For curl, a good physical example is the the electromagnetic field. We'll be discussing that it has a property that it circles around, say like a wire, so it will have a nature of like curling around that source. Now a few more mathematical terms that we need to understand is line integrals. So for a physical vector like v, and if we have a small displacement like delta L, is written this way. Now best way to understand this one is think about work done by a force F. Then work is given by F into the displacement. But when F is not fixed, so the force is not fixed across the whole of the line we're dealing with, then we take an integral across the whole line that we're dealing with. And then it is written this way. So it's from point A to B. And in case of this example like work, if the point of start and the end is same, then we can write it this way. And in the cases, this is not dependent, like the line integral is not dependent on the path of your integration, then it's a conservative, like a conservative field, it's a conservative vector that you're dealing with. For example, like the force is conservative if like the line integration is independent of the path. In case of surface integration, so when we deal with a say some vector, and then we need to understand its flux. So basically the surface integration is basically, it gives you a flux. So flux is like, so the vector into the area. Now you have a fixed area that you need to calculate. Like somebody asked you to calculate the flux in an area. Then we need surface integrations. Volume integration is for any physical, for a scalar. What happens is when you integrate it in a particular volume, it gives you an idea of, say, for a good example is like density of a substance. And then if you do a volume integration, that means how much of that material is there. So it gives you the total mass. Now, the ways to do it is there are some fundamental equations like this one here. So if, which immediately gives you this idea that for divergence, For a gradient of t, which is being like we're doing a line integration here, then the start and the end point value of that function can also give you that value. And that is why line integration ordinarily depend on the path taken, a and b. Now, if this value is independent of the path, so in case of this particular value, like gradient of t, this is independent of the path. That's what it says here. And that is true because it's a conservative force. It's a conservative uh, like vector. And in this case, this becomes zero. So it's a closed loop integration across a path. Now further, we can also draw delta V, divergence of V, a vector, the volume integration. We can convert it into a closed loop surface integration across the same surface that's closing this one. And it's called Green's theorem, Gauss's theorem. And it actually gives you that the material within that volume is same as what is flowing out through that surface, which is actually finding, which is covering that volume. For curl also we have Stokes' theorem, which gives you a curl of so it basically the integral of a derivative, in this case of a curl, over a region. So here, like sort of a surface, is equal to the value of that function across the boundary. And that gives you that this volume integration depends only on the boundary line, not on a particular surface that is being used. And if we think about the curl of a closed surface, it becomes zero for any closed surface, since the boundary line, like the mouth of a balloon, shrinks down to a point. Now, we also need to understand that we'll be dealing with some complex surfaces, and one complex system is a spherical polar coordinate. Like it will be easier to sometimes use the spherical polar coordinates instead of the XYZ, the Cartesian coordinates. So we'll be using the spherical polar coordinates r, theta, and phi. And it can be converted from XYZ, it can be converted this way. Whereas X is given by this, and Y and Z is given by this, so this diagram. And we need to know that a small volume is given by this, and an area. And the range of R is from 0 to infinity, whereas the phi is from 0 to 2 pi, which is this angle, and theta is 0 to phi. Now, then if you have to calculate the volume of a sphere of radius r, then what we do is do a volume integration. And as we have learned in vector, we use the element d tau here, and it gives you a 453 RQ. Now, similarly, we have learned in vector that we can convert the gradient in terms of spherical coordinates, divergence, and the curl like this. Laplacian is a like
d2t kind of term, which we'll also be using. Similarly, we can use cylindrical coordinates s, y, and z. And in this case, x, y, and z are given by this, and small displacement is given, and a small volume element is also given here. And the range of s is 0 to infinity, and phi goes from up to 2 pi, and z from minus infinity to infinity. And these are the forms for gradient, divergence, and curve, and Laplacian.